Hi, my name is Caden Saunders, and I'm proud to present the Ohio University Rover team. A significant portion of the work that I have done involves getting the rover to drive. Despite being a senior in computer engineering, I have worked very closely with the manufacturing team and I designed the wheels and chassis. Aside from mechanical engineering, I also designed the ROS network and set up the communication protocol between the Raspberry Pi and peripheral devices. With our novel wheel design, we are able to fold the rover up into a more enclosed space. Here is the mini rover testbed that we developed to test the communication and navigation. We were able to verify that the data path from the base station controls to the driving is functional using this simplified system. We have also started development on the navigation algorithm by using the IMU on the rover to align with a desired angle.
My name is Alex Burnett and I'm the Communication and Navigations lead.
Our autonomous navigation system consists of a GPS subsystem consisting of a U-Blocks antenna and receiver, as well as the IMU subsystem consisting of the accelerometer and magnetometer. By receiving GPS satellite signals and calculating the rover's coordinates from said signals, the rover will align itself along the yaw angle between the two locations using the data collected from the magnetometer. The rover will then proceed along the shortest possible path from one point to another, with the accelerometer providing a means of double-checking the rover's travel at the base station. Should an obstacle be detected, the rover will calculate a path around the impedance, then determine the new yaw angle and shortest path from its location to its destination. Our communication system will operate at 2.4 GHz, with a channel bandwidth of 2 MHz, in accordance with IEEE Application Notice 802.15.4. The system will comprise of 6 DigiZigbee long-range radio modules coupled with a Yagi patch antenna that each provide a gain of 12 dBi via an SMA connector. 3 Zigbees will be stationed at the base, while the other 3 will be placed on the rover, creating 3 distinct channels for information to be transferred along free of interference.
Hi, my name is Nicholas Leach. I am the ARM lead in assisting with the science module.
The arm movement is calculated with velocity kinematics. To start, the algorithm takes the values from the magnetic encoders and uses them for the thetas of the Devon-Hartlett parameters. The homogeneous transform is then calculated from these Devon-Hartlett parameters. With these values, the inverse Jacobian matrix is then solved for. Multiplying the inverse Jacobian matrix by the desired movement matrix gives the speed that each motor has to move for that time.
Shown here are the first 2 base links for the arm, designed out of GoBuilder motors and parts for easy manufacture. The third link will be a copy of the second link, and the wrist links will be made from 3D printed parts and stepper motors.
Hi, my name is Zach Takis. I'm the lead for computer vision and cameras.
For the camera system, we have 3 different camera subsystems. One of the subsystems is an Intel RealSense camera for real-time video streaming, obstacle avoidance, and object detection. The Intel RealSense library comes with their own object detection library. We will not be using this. Instead, we use the YOLO-V8 to train a model for object detection with a mallet and a bottle class. The next subsystem is using a UCAM3, which will be used for building a panorama. This camera is mounted on a gear that is connected to a servo, allowing to rotate a full 360 degrees. The UCAM3 has a field of vision of 56 degrees, allowing us to take pictures every 45 degrees of rotation. After the pictures are taken, we will use feature extraction on the pictures and stitch the pictures together.
Hi, my name is Noah Koval. I am the science lead. For the science mission, we decided to go with the zero liquid approach and instead decided to detect for biosignature gases within a soil sample. We are using a mounted linear actuator on board the rover to drill the depth needed for the mission and then using a dump tube attached to a servo to separate the testing soil from the collection soil. Once the soil for testing has been moved to its box, we will be heating the sample, and through the use of gas sensors mounted within the box, we'll be able to detect spikes in concentration compared to our baseline values of the biosignature gases.
Thank you for watching our 2024 URC SAR submission.